Notice I didn't cough on you. Little Zoom humors are. Hello, everybody. Come on in the room. Okay, I think I'm about ready to get it going here. Tonight, did you guys freeze up on me or not? Oh, some of you are moving. Okay. Lately, I've been having some trouble. My other class earlier today, I got a couple different Zoom freezes. It was kind of weird, but you're all there. Okay. Tonight, I want to keep going with chapter 9, finish that tonight. A little bit on 9.5 I want to wrap up on. Then there's 9.6. Second hour, if everything goes well, I want to start chapter 10, which is Intro to Graph Theory. We're going to talk graphs and trees for the rest of the semester. So I want to get that started tonight if I can. That's the game plan. Although I only have 18 people out there. I want a few more, but I guess I should be happy I got this many. I'm going to start this. I have a question for you as a reminder of what we did last time, a little problem to solve here. Let's see, where does share the screen? Okay. So, how many ways can you rearrange the letters of the word semester? Give it a try. Anybody got an answer yet for me?
3360.
Okay, that's one. Anybody else? Anybody want to verify that?
Yeah, that's what I got too. 3360.
Okay. All right, I'll say that's correct. So good, we'll start with that. This is the kind of problem we left off with last time. Who was it? Diksha, was that you that gave me that number? Diksha?
Yes.
You want to tell me how you got it?
So there is a 2s, right? So 8, I don't know how to say it.
Okay, well, there's 1, 2, 3, 4, 5, 6, 7, 8 positions.
Yeah, 8 letters.
So what are you going to do?
8 and 2.
Meaning, if you're gonna say a combination of two things taken from 8, or 8 choose
Yes.
2. Okay. And that would be the operation number 1, taking the S.
Mm-hmm.
Then what?
And then 3 out of 5. Sorry, 3. Wait. 3 out of 6.
I'm assuming you're now going to the E's.
Yes.
Okay, so 6 choose 3.
Uh-huh.
That's operation 2.
Yes.
Okay.
And for the
Then what?
operation 3, it's 3 permutation.
Because there's 3 remaining letters, whatever they are.
Yes.
And so that was 3 factorial?
Yes.
Okay. And that would give you 3,360, which would be correct. Okay, now that is the way that I showed it to you last time. And I didn't follow through on this, which is that, well, there's some other ways we could do this. There's some modifications on this. Your book does discuss this. Your book in section 9.5 has a section on solving these kinds of problems, and then it extends it a little bit to show you another way that, in my opinion, is actually easier and more intuitive than this one. But the book has a reason. They want you to get used to thinking one operation after another in sequence, and you find out how much in each one and multiply. So it's a strategy that's effective. So even though there might be some shortcuts to this, they like to talk about it that way. But I want you to see the shortcuts here. So if I may, I'm going to do this slightly differently, okay? That at first I'm going to do it a longer way, then you're going to see what I mean by the shortcut. So I'll repeat what you have here. You got 8 and 2, 8 choose 2, operation number 1, that's for going for the S. Then there was the 6, 3, and that was going for the E. So those are the repeated ones. Then the next letter that's not repeated is M, and I'm going to act as if that's all I'm doing. And what am I doing with the M? I'm trying to figure out where to put it. I have, well, let me write it over here. You have 1, 2, 3, 4, 5, 6, 7, 8 positions. And at the beginning here, what you're doing is you're saying from those 8 positions, choose 2 that'll be filled with an S. Now, those 2 are taken, you're down to 6 positions. Choose 3 of them to put in an E, because the E doesn't matter where you put it, they're all the same E's. Now the M. I've only got 1 M, and I've got 5 spots. No, I'm sorry. There's 6, I've taken away 3, so 5 are used up. There was 8 total, so I'm down to 3 places to put the M. But I could be systematic and say the next operation is from 3 positions, pick 1 to put the M. I mean, that's dopey. I could do the 3 factorial here. It's faster for all the remaining unique letters, but I have a reason. Okay, next, after M, there's a T. I'm down to 2 positions, choose 1, and that'll be where the T is going to go. And then there's an R. There's only one spot left, and I've got one to choose from, and there's R. Okay. Now, what I want to do here is to, and this is to remind you of what the formula is, because you can take this 8, choose 2, and put it right in your calculator and get an answer and forget what was the formula originally, because it's too much hassle to use the factorial mess. But it's worth it for this problem to review. 8, choose 2. The formula says take 8 factorial and then divide by 2 factorial, that's the R, and then n minus R, which would be 6 factorial. And then what are you going to do? You're going to multiply by 6 factorial divided by 3 factorial, that's R, and then 6 minus 3, 3 factorial. Stop and notice something. The 6 factorial cancel. And why do you have 6 here? Where did that come from? By saying I've got 2 from 6, I'm left with 2 from 8, I'm left with 6. The same multiplication, 8 minus 2, that went down here, you use to find the 6 factorial up here. And that will continue. The next one, 3, choose 1, so that's 3 factorial. And what's down in here? 1 factorial, 3 minus 1, 2 factorial. Then 2 factorial. And down below, 1 factorial, 2 minus 1, 1 factorial. And lastly, 1 factorial, R is 1 factorial, 1 minus 1 factorial is 0 factorial. But 0 factorial is 1. Okay, now watch what happens when we clean this up. The 6 factorial here reduces with the 6 factorial up in the numerator. The same for the 3, the 2, and the 1. What are you left with? 8 factorial divided by how much? 2 factorial times 3 factorial times 1 times 1. That's not worth writing. Okay. Now, I claim that I didn't need to work this way. I could have understood the problem using this and gone straight to this. Let me show you why. What's up here is the number of ways to permute 8 letters. No matter what, whether there's repeats or not. Suppose they were all different. Or I thought of them as little tiles in a Scrabble set, and then the 3 M's were different somehow. Now what's down below? That's the number of ways to permute, or I could have said rearrange, the repeated letters. I have an an S that repeated 2 times, and I had E that repeated 3 times. The number of ways the E's can be rearranged is 3 factorial. The number of the ways for the S to be rearranged, 2 factorial. And I'm just dividing out. So it's actually a cleaner, intuitive way to think about the problem. If you go look in your textbook, you're going to find this at the very end of chapter 9.5. There's a theorem 9.5.5, which they don't prove, but they just present it to you to say that you could use this method instead. On a midterm, on a quiz, I don't care, I mean homework, you can go this way or this way. Now the advantage of, hold on here, of this one is that, I forgot a third operation here, is that they are really trying to get you guys to think about operation followed by operation, followed by operation, and just multiply the number of ways for each one, because it's generally safer and it's a good way to think about a lot of different kinds of problems. But for this particular problem, it's easier to think, how many ways could I rearrange no matter what if I have repeats or not in here, get that number, and then divide out the number of ways that I could have changed around the ones that repeated. That's what's happening down here. So there you go. I'm throwing that out as an extra formula that you can use if you want to. Your book doesn't dwell on it too much, but there it is. Okay, so that's one piece of 9.5. That's one of the things I wanted to do here, was to continue with 9.5 with a couple small things. There's this one, and there's one other idea that I want to lay out here that is in the reading of the book, and I think there's one homework problem that does this. And I want to add a little something to it. Your book doesn't give you this formula. Okay, this is called a circular permutation. And I'll try this now. Suppose n people are arranged in a line. Let me just call this number 1 here. How many ways? You have 8 people, and you're going to put them in a line and rearrange all the different possibilities. How many ways? Sure, somebody has to answer me.
N factorial.
N factorial.
Exactly. Right? Because you can think of it as the first position in the line n ways. Okay, the next one is n minus 1. The next is n minus 2, and so forth. Or that's just the rule for how many ways to permute objects, right? Now, number 2. Suppose n people are seated at a circular table. Or I could say n people are put in a circle to hold hands or something like that. How many ways? Is it the same? Here, you've got a line, and you've got n positions. Here, you've got a circle with n positions. You would think it's the same.
No.
Yeah.
Oh, good. A yes and a no. Who's going to go with the no?
I think it's more than n factorial with the circle,
More. Why?
because with the line we have the start and the end, and with the
Okay,
circle
hold
we
on.
do
There's
not
a
have the,
start, and then there's an end. Okay, I'll buy that.
and with the circle we do not have those things like
You don't really have a start and an end, but you have a first and then going around, then there'd be the next one after it would be the last one. So you could say this is the start, come around, and then there'd be an end. As if you took this line up here and just joined them like that, you see? But here's the problem. You can start anywhere. Like suppose the first person that goes here, I'll let it be Sammy. Okay, he's sitting there. And then next to Sammy will be James, right? And other people going around. But what if I turned the table and everybody say, you know, they're all on a rotating dais or something, they can all rotate? Then Sammy would be here and James would be here, but it'd be the same arrangement. What I'm trying to say is, you're right, Sam, it's not the same as n factorial, but it's not more, it's less. Because you have to subtract, not subtract, you have to remove, divide out the different places that someone could start and then sit down. For any arrangement of people going around, you could imagine just turning them in the circle here, and there'd be n different ways in which you could put the same arrangement. I don't know if I said that very well.
Can you say it again, please?
Well, first let me give you the formula. N minus n factorial divided by the n ways that the initial person could sit at the table. It winds up being n minus 1 factorial. Okay, let me try another way. I've seen these problems show up in different ways. Suppose it was not people, but different beads with different colors or whatever on a necklace. How many ways can you arrange them on the necklace? Meaning you can turn a necklace. You can also do this. You can go in your book and read on it. There's in section 9.5, they try to give a better explanation maybe than I gave. Anyone want to try to help me on this? Explain it? Anyone listening to me? It's all quiet out there tonight.
I can try.
All right, Max.
I don't know how well I'd be doing it as opposed to yours, but I'm imagining in a linear arrangement, the equivalent, there's an equivalent operation going on. In a linear fashion, you, let's say you take the person off the end, put them at the beginning, and shift everyone down, right?
Okay.
That'll be a different arrangement. Now, say you did the same thing with the circle. You took someone from the start and put them at the end. Well, that's the same spot. And then you shift them down. Nothing changes.
Okay. You're kind of thinking like, maybe I'm wrong here. When you're saying shifting, it's like, are you thinking about arrays and moving things in an array?
Yeah.
There's
Yeah.
something like that. Okay. So if you, like you said, this person moves over to here, then the person in the end has to be put here.
Yeah.
In a line, that's different. But in a circle, that's not. That's just moving. This person here moves over to here. And then everybody gets to shift around, and the person at the end just follows through and is still coming before the person who started. Let me try it again.
Oh, so that what I'm understand like in a circle we have one case less than the line.
Yes.
Okay. Okay, I got it.
That you start by saying it'll be like this. The first person sits down, there's n choices, then the n minus 1 and so forth. But the fact that you've got it joined in a circle like this means, and I think Max was good on that one, if I said this is the first person, and now I'm going to put the first person over here, everybody else can just shift over one and you'll have the same arrangement. But you can't do that in a line. If I move this person over to here, then everybody moves down one and a person at the end comes over here to start, and that's a different arrangement. Okay, now, well, I'm gonna let you guys think about that, but here's how this works. If it's we call it a circular permutation, then you figure out what it would be if it wasn't a circle. That would be n factorial, but then you have to decrease by the number of ways where that first person could be located, divide out by n. Now, this is what your book gives you. Most textbooks will go one step further, and they'll actually try to prove a theorem on this. So let me try this now. Number 3. Suppose R from n people are arranged in a line. How many? Well, now this would be the permutation of Rn, right? Do you remember the formula for that? I won't think I'll write it down, but the n factorial over R minus n factorial. Because imagining that I had 20 people and I have to pull out 5 of them to put in a line and rearrange any way I wanted to. Instead of the whole group, I take a piece of the group. Now, 4. Suppose R from n people, or objects to make it more general, are arranged in a circle. And I probably should have said how many arrangements here. I got lazy. This would be the number of permutations Rn here, but divided by what?
N.
Not n.
R.
R. Because think about this circle here. I don't know how many I put down here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There were 10 initial positions here. And imagine I'm taking it from 20 people. I'm just grabbing 10 and seating them at a 10-person table. Well, it'd be the 10 that I'd have to divide out for the rotation effect. Okay, well, this was extra. This was just letting you know that this is a very common thing that you come across in books on combinatorics and discrete math and how to count things. Your textbook didn't give you this one, but they mentioned this one. And I think you have one homework problem where you have to deal with a complete circle with all the people. And then they're going to have some conditions on it. You'll see when you get to that homework problem. So those are 2 extra things that I did not cover last time in 9.5. We're going to move on to 9.6 shortly, but I just want to wrap that up and let you know about those things. Now, about homework. I had a couple people email me, wanted to say, well, what exactly, where should we be at in the homework? That there's, I didn't check to see the numbered assignments, but by the end of this weekend, your goal should be you have finished 9.6. I'm going to start chapter 10 tonight. You might even want to start getting into that. But 9.6, I have posted an online assignment for you. It is a 10-question quiz, it's called, in there. And you get multiple attempts to try it. And what I've done is I've written 10 short answer questions, number answer questions, kind of like these here, or to say this one here, where you have to give me the exact number answer. Some of them they're all integer answers because they're all counting problems. Some of the numbers are relatively small. Some of them are in the millions or so. But you better put the exact integer in to get it correct. And there's 10 of those questions to practice. You can try it anytime between now and Monday night. And
Question.
the answer's on Tuesday.
Are they case sensitive, like commas and such, or?
Oh, I think it doesn't care. I think if you put it in, this is regular. Every night this thing goes off. You can type in commas if you want, and if you don't, it'll put them in for you. Okay. So That's the news. You have an extra assignment to do. Because I really want you guys to keep up with homework, and I'm figuring by giving you this assignment, you can see what I'm expecting from you in terms of being able to solve counting problems. What I often find is on the third midterm, the toughest problems are the ones involving the counting, and people need more practice with that. So I'm trying to give you more. Okay. I'm ready to move now. I want to talk about 9.6. In a different kind of counting situation where there is a formula that doesn't feel intuitive or natural. Once you know the formula, you're going to be able to solve the problems that you have to do, but understanding where it comes from is a bit tricky. So I want to spend a little time developing the formula for what we're about to do. This is 9.6 now. And you're going to be counting what are known as multisets. And another way to say it is you're going to be dealing with R combinations. I don't know, 10 choose 3, for example. But with repetition allowed. That will make sense when we get into the problem, okay? So, recall. If I write this, N choose R with this notation, oh, I've got to remember, there was another way to describe it. Remember, it was the binomial coefficient. You'll see that every once in a while. We're just thinking about the number of ways to find combinations. So N choose R would be what? The number of, someone want to give me a word description? Instead of me? Volunteer.
Total number of permutations?
Not permutations. Permutations involves rearranging, ordering.
Are combinations of n objects?
Okay. So sorry, this number of what? Say it to me.
Are
And combination.
combinations of n objects?
Are combinations of n objects? No. I would say selected from n objects. The idea being that you've got a large group here that you can pull from and select from them, and how many are you going to take is R. So do you see that the amount R has to be, excuse me, less than or equal to N? You can't take more than you got. So we want to be careful in the words we use. The number of R combinations selected from N objects. Okay, but combinations is including an idea that I would like to make more explicit. Combinations means order doesn't matter. When we use the word permutation, then order does matter. That the arrangement of the same objects taking the same objects but arranging in different ways would count as different things. When it's a combination, you take those objects and it really will not matter how you arrange them. There's only one way to grab those R objects, not caring where you're going to put them. That's the big difference. Now, I'd like to write this a slightly different way. Or the number of subsets with size R of a set with size n. So you have a set of objects, large set here with n objects in them. And what are you going to do? You're going to find a combination. You're going to take out of that R objects, but those R objects would form a subset because subsets, sets in general, do not make any distinction about ordering. That when you write down a set like set A, B, C, if you wrote A, B, C, it'd be the same thing as C, B, A, because we don't care about the ordering of a set, recall? So I can use set language in here if I wanted to. I'm doing this on purpose. Because now I want to go beyond this and say, that's what a combination is about. It's how many subsets of a particular size I can pull out of a larger set n, size n. But what if the R was bigger than n? You needed to select more objects than you had in your original set. Consequence, repetition must occur. And we no longer are finding subsets. Instead, you find what are known as multisets. It's a new term now. A slightly different version of a set. A multiset is a collection of elements with repeats. Example, A, B, C, C, C. Notice that we use set braces here, but it's not a set. It's a multiset. It has three essential elements, A, B, and C, but we're indicating that A is repeated twice and C is repeated 3 times. We're just creating this new object to handle the problem now of saying, well, what if I have to find out how many ways can I take 10 objects when there's only 3 to choose from, but I can get repeats? That's the kind of problem we want to tackle now. That supposing your goal is, how many do I have here? 1, 2, 3, 4, 5, 6 objects in my multiset? And I can grab from boxes of A's and boxes of B's and boxes of C's. And I can have as many A's, B's, and C's as I want to, but I need 1, 2, 3, 4, 5, 6 elements in there. How many ways can I do that? Well, one way would be to have all A's. Another, all B's. Another, all C's. I could have 5 A's and 1 C. I could have 3 A's and 3 B's and no C's. You with me? How many possibilities now? That's a new kind of counting problem. Order will not matter though. So it's like a set, it's just we get to repeat some elements. So I want to develop now a strategy for solving that, okay? And I'm going to do it by example. Number one, let S be a set with A, B, and C in it. Actual set, not a multi-set. Now, how many ways to select 6 elements where repeats are allowed? Let me give you, to start this off, let me just write some of the things you could get. You could have, what, let's see, A, B, B, and then a C. 6 elements, repeated some A's, repeated some B's, and 1 C. What about this one? A, C, A, C, A, B. Different? One more possibility. Now this one is not like this one, because you notice that in this one I had the letters in order. There's the A's, there's the B's, and there's the C's. Well, let's suppose that I would like to write all of my possibilities with the letters in order. So what would I do on this one? What would happen here? I would have A, 3 A's. I got a B, and then there's 2 C's. Note that these are the same because order does not matter. Leading up to something. I gave you 2 examples here. In the first one, I nicely put the letters in order. In the second one, I did it, but I wanted to show you that I could have. And for any possible multi-set that I'm going to select from here with 6 elements, I could write it in this order if I wanted to, and it would be the same as whatever I actually grabbed, because order doesn't matter. Now, I'm ready for a strategy. Consider the special order where all similar elements are grouped together. But now I'm going to add a twist. separated by bars. So this one up here, for example, would be AAA bar BB bar C. This one, AAA bar B bar CC. Now, by this new strategy, instead of writing it in a fancy multi-set way with commas, I'm writing it as basically a string of characters, where I have a character for each possible element, and I've included 2 new characters, these bars. Now, for every one of my multi-sets, would you agree I'm going to have 2 bars?
Yes.
Because I want to separate the possibilities out. Watch this one, for example. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 8. I needed sets of size 6, right? Multi-sets. Well, where's the B and the C in here? I have to indicate that there are none of those with 2 bars with nothing between them. I can still do that. What about this? One, 2, 3, 4, 5, 6. That's giving me also a picture of what's going on. And all of these are different, and each one could be pulled out and rearranged in another form, but those are indicating now all the different possible multi-sets by this new strategy. And for every single one of them, I will always have 6 characters here that represent elements of the set and 2 bars because there's 3 elements in my original set. A, B, C. What if there'd been A, B, C, D? How many bars would I need then?
3.
Okay. 1 less than however many elements in the set I'm pulling from?
Mm-hmm.
Okay, we're getting somewhere now. We're now going to generalize. One, 2, 3, 4, 5, 6. Okay. Every multi-set is a string of crosses and bars. And your problem becomes how many ways to create a string of 8 characters using 6 crosses and 2 bars. I don't have to worry about the individual A, B, C, Ds. All I know is I can put them together somehow. Whatever one element is, this group would be over here. I don't know what it is. I'm just going to put XXX for 3 of that group. Then I'm going to have 2 of the other group, and I'm going to have 1 of the last group. Separated with bars. That's it. The bars are letting me know that there's 3 choices to make from the set. And this is how many is going to repeat for each one of the choices. I don't have to care what the actual values are. And now I just want to know, how many ways can I make these kinds of strings? Strings that have 6 X's and 2 bars. If you think about it now in terms of positions, or how many ways to position six crosses or X's in 8 positions. That's a simple combination problem now. Eight, choose 6. Okay, I don't know. It's weird to be zooming and not seeing faces, so I don't know if you get me or not, where we're at, but that would be my strategy for handling the original problem of, what was it? I had 3 items in my set, ABC, and I needed to get a group of 6 from there where I'm allowing myself to repeat. How many ways to do that? I've argued it's 8, choose 6. And let's just look and see, where did these numbers come from? What was the 6? That was the size of the set that I had to pull out. That would be how many objects I need to get out to select. In the language you've been using, that's R. Where did the 8 come from? Well, I had 6 elements in my multi-set. That was the R. Plus what? 2 positions for the bars? But where did I get the bars? Where'd the 2 come from? Because my initial set had 3 elements, and I needed 2 bars to separate out those 3. What letter do we use for the initial set size? N. So N minus 1 is where I would get the number of crosses and bars. And I'm there. I went through all of this to give you a formula that you can now use. Let me present that, and then we'll solve some problems with it. Okay, so now I'm there. General formula. The number of ways to select R objects from N objects when R is larger than N. And repeats are allowed. Is R plus N minus 1, choose R. That's the magic formula. What I find is, in the past, where if I had stopped and just said, here's your formula, let's do the problems, people had no problem doing the problems, but to explain where this formula comes from is tricky. It's not intuitive. It's a strange one. Okay. And this is called the multi-set formula because you're finding multi-sets. And I wanted to explain all that before we actually cranked out some answers. So let's see. I'm going to try now a problem from your textbook, and this would be my example number 2. Doesn't matter what textbook problem is. I'll just write the info down. You have 8 different types of batteries. Part A. I should add this, 8 different types of batteries and a large supply of each, meaning you can get as many as you need of any type. The shelves are not bare, they're fully stocked. How many ways to choose 30 from the 8 types? Just plug into the formula. The number of objects you can pick from is 8, but you allow for repeats. How many do you want? 30. So you go straight to the formula. R 30 plus 8 minus 1 over 30, or choose 30. Boils down to 37, choose 30. And I even wrote the number out on this one, it's huge. That's 10,295,472 ways. So there you go, a multi-set formula. Very common problem is how many ways to take multiple values from a given set of objects, where you get to have repeats, like you go to a store and you need so many of this and so many of that. I think one of your homework problems kind of like that, where you got to go to the donut shop and there's 6 different kinds of donuts and you need 3 dozen. How many ways can you do that? Let's see. Ooh, before we go on break, let me throw another version of this and then we'll take a break. Part B. How many ways to choose 30 from 8 types but include at least 4 AAA batteries? So imagine you got a box and you're going to fill it with batteries from these, and you got 8 different cartons of batteries, and you're going to fill it up till you get 30 batteries in your box. But you must have at least 4 AAAs in there. Anyone want to give me a strategy, or should I tell you? James, you're unmuted. Oh, no, darn it. I thought he was going to talk to me. I can't hear you. Oh, well.
Hey, can you hear me?
Now I can. Who's there?
It's Tristan. Hey. I would guess that we would just place the 4 AAA batteries and reduce the value of R by that, so we can say now I only have 26 for R?
So my first operation would be to take 4 AAAs. Thinking operationally. First thing you're gonna do is get those 4 so you're guaranteed, right? I agree. How many ways to do that? 1. And then your operation number 2. Take the remaining.
Yeah, and that would be what? Using 26 as the R value for that new equation we have?
Okay. So your R is 26. What goes up here?
26 plus 7? Or would you still be adding 8?
It doesn't say you can't have more. It says at least 4. You could have more of those AAAs.
Oh, all right, yeah.
So I would just say plus 8 minus 1. And that simplifies to 33, choose 26. And my notes tell me that winds up being 4,272,048 ways to choose batteries.
What if that was not at least or at most or something like that?
At most?
Yeah.
Funny that you would ask. That was the next question, part C. At most, I had it at most 3, but you know what? It's break time. Can we come back and do the at most afterwards?
Sure.
All right. Let's take our usual 15 here and we'll come back. All right, guys. At least I got a few thumbs up. I know somebody's out there.
Yeah, sounds good.
Let me turn on the timer. Hang on. I can chat with you once I get the timer going because
Gotcha.
I want to make sure we don't use too much time. All right. What's up, Tristan?
I just got back from finding a lost dog. There was a dog lost in our neighborhood, and
That's your excuse for being late?
yeah, it is. I swear to God.
At least you didn't eat your homework.
Yeah, right.
Okay.
Yeah, we found it. We found the owners. It was a little Chihuahua hiding in the bushes.
Mm-hmm.
Like the owners were like 6 blocks down. Small dogs can't get a very far distance in like a long time.
You know, I live out in the country, so there's no neighborhood for mutt to speak of where I live. But I don't know what it's like now where there's neighborhoods around you guys. Is it spooky quiet or a lot of people out walking around? Is it normal or is it weird?
I would say that the demographics, Travis, I would say that demographics for my neighborhood is like everyone's outside. We go on one daily walk, the family, and on the walking pad near our house, maybe we'll see like 200 people.
Oh, wow. Okay, so and are they distancing or are they not?
Yeah, it's
Masking
complete.
or-
It's I would say probably 60% of people are wearing masks. There's the occasional maskless jogger that's jogging down the bicycle pathway, but in my neighborhood, the bicycle pathways are shut down to bikes.
Yeah.
So there's like 8 feet to walk in each like paved road. And then you can like still walk on the ground next to it. So yeah, it's like not that hard to stay 6 feet away from somebody if you're walking. But yeah, a lot of people are out.
I've been quarantined, been sort of self-quarantined. I'm not sick, but I don't need to go out. My family's getting the food. They're going shopping. I'm just hanging out of the house. There's just fields and vineyards around me, so I just go out there.
Where are you at?
Out West County way. So it's comfortable here.
Yeah. That's
And it's not. I mean, this is my normal lifestyle here to be the hermit that lives in the little quiet place. So
yeah.
I'm not missing people.
I don't know. I lost my job, so I've been out of I've been just
Oh, that's a bummer. Okay.
aimless for like the past 2 weeks. I think it's been 2 weeks since I officially got cut. But yeah, the company, the Keysight, the company I was working for, is just like taking a severe downturn
Bummer.
because they can't manufacture anything. They're not deemed an essential business, so they're shuttered. And I'm not technically their employee because I'm a contractor. So
Right.
they're like, yeah, we're not going to pay you. And it's within their legal right, but it still sucks. They're like, we'll call you in like August if things open back up.
August. Wow, not June or something. Man.
Yeah, they said
So
August.
are they thinking that they'll be gone down all summer?
They're thinking they'll be done. They'll be done until fall. Yeah.
Man.
The CEO is not taking any pay. The vice presidents are taking 25%, and then the senior management is taking a 10% reduction. At least that's the last I heard.
Have you guys, just in general, I don't know if anybody's listening here, but I haven't checked the summer schedule. I didn't know what the JC is saying is going to happen.
For fall?
Summer.
Oh, for the summer.
I saw, I didn't read the email, but there's some summer schedule out there.
Yeah, I think
Sorry.
fall semester got postponed for sign up, but summer was still open for registration.
Was it all online?
I mean, it's not officially online yet, but
Yeah.
it's going to be online for sure for summer at least, if not.
You guys are all planning on being online?
Yeah, and my buddy goes to San Jose, and it says like they already sent out a letter that fall is going to be online there. So yeah.
Yeah, I mean there are certain classes. Yeah, Cole, I agree with you. There are certain classes right now that I saw that are in person over the summer, but there's not a lot.
What about you guys who are going to be transferring next fall or planning to?
My university said that they're still taking transfer students, and they're assuming a normal start to the semester.
Anybody else out there?
Yeah, that's me.
Yeah.
Yeah.
What's happening with you?
I got waitlisted a couple of places, and mostly I might go to SF State, but I got waitlisted a couple of UCs. I would not find out where I'll go until June or maybe end of June. But yeah, it's going to be online, I guess. But if
I'm just curious what's out there. If everybody's expecting just to go, if you're going to transfer to some place, but you can stay in your house.
Yeah, that's going to be the case, I guess, because I think most schools are going to be online. Like they're preparing to be online.
Yeah, I think for Santa Cruz, they're like, I think someone mentioned that they're going to attempt, or they have the goal to do maybe partially online and partially in person, depending upon, when the time comes, they'll make the final decisions and such. But if it does come to them, doing some in-person classes, they'll say like people that have room and board, they'll just give them a full refund and they can just go about their way back home or wherever they're from.
If they did have in-person face-to-face classes, would you go?
Oh, I would definitely go. Yeah.
Yeah, I would.
Yeah, sure.
Really? You're not afraid?
I mean, the death rate now essentially for people our age is like 0.005%. So,
You're not going to take it home and give it to grandma?
I don't live with any extended family and have no contact with anybody else but my wife and kid. And they don't have contact with grandparents either. So,
you're going to give it to this grandpa right here.
Well, I'm never going to see you again, Stir, so we're fine.
Oh, yeah. No, I meant that's one of the issues for older faculty too, is what are they going to do about that?
Oh, yeah, you're right. I don't know. I mean, honestly, that'd be the number one case for like why I wouldn't want to do an in-person class would probably be for like the professor's sake, I guess.
Well, they just wouldn't be there. They'll be online.
Yeah.
Just get a hazmat suit.
Yeah, it's spooky, weird. I don't know.
I'm not quite a hazmatter yet. I probably have optimism bias about all of this, but
yeah. Well, hey, I'm going to take a short break here, guys. I'll be back in a bit. Let me get
All right,
the mute
bye.
button here. And I'll see you.
Hey, Karan, are you still out there? I can't hear you. If you are. Karan?
Yeah, what's up?
Hey, yeah. So you said you got waitlisted at a couple places. Where do you get
I got waitlisted to Santa Barbara and Irvine.
Yeah, I got waitlisted at Santa Barbara. I got waitlisted at Berkeley and Davis.
Yeah, I got rejected from Davis.
I got.
And then where did I else got rejected? Santa Cruz also I got rejected too, which is weird because how did I got rejected from Santa Cruz, but I got waitlisted to Santa Barbara and Irvine? So I kind of didn't get it, but whatever.
Right. I mean, like my.
Yeah. But yeah, I think I got also rejected from San Jose. And,
Oh yeah, I got straight rejected from San Jose. Yeah.
Yeah, I remember we were talking about it in class, but yeah. And then most likely, if that doesn't happen, I'm gonna go to SF State, I guess.
Okay.
Yeah. What's your top school? I mean, did you apply to CSUs or no?
I did. I applied to some CSUs. I got into.
Did you apply to Cal Poly?
I did. Yeah, I got straight rejected.
Okay, I didn't apply there because I didn't thought it was gonna be a shot for CS.
Yeah, it's really. I mean, it's every major is really impacted there. I think, except for like a few.
I mean, I think it's like CS and engineering is always hard for.
Yeah, especially.
The rest of things people don't get that, but yeah.
Well, my wife she got accepted straight up into Stanford and Berkeley, but got waitlisted at Santa Barbara and
Stanford and Berkeley. Wow.
Yeah, and then she got waitlisted at UCLA too.
Wow. Okay.
Yeah.
It's kind of weird because I think last year San Jose messed up real bad. I was talking to them and they were like,
they didn't get any transfers.
With like 3.0 for CS, and now they just changed it to 3.9.
What? Say again.
So last year I was looking at the requirements and they were accepting people at 2.4 for software engineering, and they were like accepting people with like 3.0 for CS. And now this year it's only like they just bumped up to like 3.8, 3.9 for everything. They're like some people. I think I heard from one of the people like someone got into Berkeley and didn't get into San Jose. It's like okay. So it's like I don't know. CS is such unpredictable, I guess, at this point.
Honestly, dude, I just feel like there are geniuses and there are morons in like computer science, and there's like no in between.
This is weird. I mean, yeah. But we're gonna go though.
Yeah, I'm leaning towards UCSC. I mean, like I don't know. I got waitlisted at a couple places, but I don't know why they just didn't straight up reject me. Like they got so many transfer applications.
Yeah, but did you you got waitlisted for Santa Barbara, right?
Yeah, I don't think I'm gonna get in there either.
Yeah, but is it like computer engineering or computer science?
It's computer science. I believe it's their BA, but I haven't really looked too much into it. I forget what I applied for all.
I see.
Did you guys tag at any schools? Or
I think my tag got rejected from Santa Cruz for some reason. They said I had like poor English grades because I was like kind of new to this country like a couple years back. So.
Okay, gotcha.
Yeah.
I don't know.
Yeah, I don't know. Does Davis even accept tags for CS?
They do actually accept tags,
okay.
but it's they kind of stratify their degree programs by having the computer science and engineering degree, and then just the computer science BA,
right,
Bachelor of Arts.
Gotcha.
So you can't really do computer science there without doing computer engineering, is from what I understand.
Okay, so that probably filters out a lot of people who just don't want to bother doing the physics and stuff.
Yeah. So I think there's actually a lot less math that's required for the BA one. I think Math 2 and Math. I think
for most CSUs, they're only required for Math 2 for CS actually.
Oh yeah.
Yeah.
But I don't know. Davis has had a lot of transfer students this year too. I think they said they had 19,000 transfer applications this year.
That's a lot, actually.
Yeah, just for fall, not even for the whole year.
Yeah.
They accepted 7% into the computer science major.
I was looking at last year, and last year was kind of, I think everywhere I was looking at CS, it was less than like 6%, 7%, I guess.
Yeah, it's really insane. I mean, the market's gonna be saturated for sure. I don't know. I'm not too confident about my marketability when I graduate.
I mean, the school, I mean, sure, it's important, but it's like after you get your first year, 2 years of experience, then everything becomes a lot easier. You just need an internship at least, so you
Yeah,
get a
right.
big boost. Easier
I
said
mean,
than done.
I'm just worried about like I've applied to so many internships and I'm just like completely getting overlooked because I'm not going to be finishing within the time frame. I'm just like, hey, I have at least 2.5 more years to finish my degree. I'm transferring, and everyone just like, nah.
Yeah, it's rough. I mean,
Yeah.
at least you're not one of the people who got an internship and then this whole coronavirus thing.
Oh yeah.
Yeah, I mean that's pretty rough.
I feel it's
That's
just like in
devastating.
Sonoma County. I feel if you go to Bay Area, there's gonna be a lot of internships for you. Sonoma County.
Yeah, I don't know. It's like being in the Bay Area too. I just find the Bay Area very depressing. Like,
I mean, yeah, no,
I
I
feel
feel
you
the
there,
ID
man.
jobs. I'm just saying ID and like CS, all jobs are more there compared to here.
yeah, I
Dad is in like IT, and he never gets jobs here. He always has to go to San Jose and stuff.
yeah, that's what I'm saying. I feel like I'm gonna be doom and gloom about my business prospects because I know if I want more opportunity, I have to go to a place I don't really want to go to. You know?
Yeah, there's a reason a lot of people commute to SF instead of just living there because
Oh god, dude, it's brutal.
it's brutal, but it's worth it depending on what you're looking for.
Yeah, experience. I mean, the first 1-2 years, like you can put in 2 years into some place in SF. I feel like. Anyways, Stir's back, so let's focus
I'm
on
back.
him.
Time to start up, guys. Well, the bell hasn't rung yet. We're just about there. Let's see what we got to do here. Okay. Bing bang. Okay. We got one more of these to try. The rest, I mean, there's some good problems in the homework. You'll see how to do them, but I'm going to give you one more attempt at this here. So this was C. The same battery setup here. Choose
Green.
30. Is the screen on still?
We still have the alarm.
Yeah.
Oh, my bad. How about that?
All
Choose
good,
30 from 8 types.
I want to go back to Cole's or Travis's comment.
No. Include at most 3 AAA batteries. So this is not at least, this is at most. So now you rethink it. You say, what does it most mean? Well, you could have 3 AAAs in there.
But it could be 1, 2, and 3, right?
Or 0.
Or 0, yeah.
And for each one of those, there'd be no overlap in the possibilities of these, these 30 batteries. They'd be different. So it's a way to partition the set of objects that you would create here, the set of multi-sets here. And so you can use the addition rule. You can say, how many ways can I get a 0? Add to that, how many ways for just 1? Add to that 2, add to that 3, and that would be it. You can use that addition strategy. Or I'll say, divide into cases. Zero AAAs. All right, how many ways for that? You don't have any AAAs, So there's 30 batteries you have to get. So your N is 30, but your R is, I messed it up. Oh, my bad.
R is 30, right?
Yeah, my R is 30, but your N
Is
has
0.
gone down from 8 to 7. So 30 plus 7 minus 1, choose 30, which would be 36, choose 30. Plus now 1 AAA. Wait a minute. Technically, aren't there 2 operations here? Your first operation is grabbing 1 AAA and put in your box. And if I want to be fussy, it's 1 choose 1. Sorry, I'm a little sloppy about that. So you choose or select 1 AAA. Now what do? Your next operation. You got 29 batteries left. And you're choosing from 7 types because there's no more AAAs. And you would get this. 35, choose 29. Next thing, you're going to get 2 AAAs. So you go to the AAA bin and you take your 2 of them. There's only one way to do that, but if I want to be fussy about writing this out, I would say what you're doing is choosing 2 from 2. But that's just 1. And now you're down to what? 28 batteries from 7. And this simplifies to 34, choose 28. And one more. Take your 3 AAAs. One way to take 3 from 3. And this is 27 plus 7 minus 1 over 27. I'm hoping you see it's get routine now. And now you plus 33 over, no, choose 27. Okay. And in the end, you get 6,023,424. Now I worked kind of hard here. Did anyone think, why is he working so hard? Because there's an easier way? Here's your other option. Or you find the total ways to choose 30 and you subtract the ways for at least 4. AAA. Think about that. What I have here are the ways you can get 0, 1, 2, and 3 only. If you didn't have any one of these, you'd be in the category of having at least 4. And we did this last time. This one was part A. So how many ways to choose 30? It boiled down to 37, choose 30. At least 4, that boiled down to was 33, choose 26, and you get the same answer. Pointing out to you that sometimes with counting problems, you can find alternate ways to do the same thing. If you're confident that that made sense, then you should get the same answer, and you do. Okay, that wraps up what I had prepared for you guys in terms of the accounting chapter here. That was 9.6. You have online now 10 questions to play with. Try to solve between now and Tuesday, practicing these ideas. You also really should get into the homework and see if you can make the answers come out the way they are in the back of the book if you got the strategies down. That we've covered quite a few different strategies here. Next week on Tuesday, I'll be taking your questions if you have them and reviewing with you. But I got to keep the train moving along here. We want to get to discussions of graphs and trees and algorithms involving those. So I need to start tonight with the time we have left here to get a intro lesson going on graph theory. So that's my goal. We're good? Ready for me to move on then? I will say I'm going. If there's any comments. All right. Let's see. I have, it's on paper, but maybe I could post it if you care. But to get the graph theory section going, I have this prepared little PDF file that I printed out just for the heck of it, because I would like you guys to get a sense of how important graph theory is. I'm guessing many of you already know this, that there's a multitude of applications to what we call graph theory. I can't get this on the same screen. Oh, well, I'll just zoom in like this. That graphs show up in so many ways nowadays because of the power of computers, the internet, etc. That you find graphs, as we understand graph and graph theory. Graph does not mean an XY coordinate system and you're going to be plotting functions and putting points down, not even 3 dimensions like you might have done in 1C if you had that class. It's something different, something very powerful that has many, many applications. And I just give you a taste of it here, my little intro paperwork here, that you find applications in social networks and networks for economic structures, biomedical, obviously on the internet, information networks, and neurons. I mean, that's really big nowadays, neural networks and so forth. Underneath all of that is graph theory. And we want to explore just the foundations of graph theory. And I had a couple examples here just to give you a taste and give you some images to go along with what we're about to get into. A computer network with multiple links between data centers in various cities connected by what we're going to call edges. The points, the cities will be the vertices of our graph. Our graph always has a collection of vertices and edges. The edges may or may not be directed. It could be that there is a flow from here to Chicago in one way, or it could go both directions. Depends on the nature of the graph. Well, this, an acquaintanceship or friendship graph.
That's way too many, right?
Friends?
I mean, never mind.
What? Come on.
I have no friends.
Well, sorry, you're not on the graph, obviously.
I know, it's hurtful.
You can represent whether two people know each other. That is, whether they are friends in the real sense or the Facebook sense, if you want, social networking sense. And you can connect people that way. And then you can analyze the situation with that with the same language, edges and vertices. We can talk about the degree of each vertex. We can talk about other features of this graph once you get some knowledge. An influence graph. Studies in group behavior. It is observed that certain people can influence the thinking of others. Did you know that? A directed graph called an influence graph can be used to model this behavior. Notice the new word in here, directed graph. Now in this graph, you're seeing arrows. So what does this mean here? That Deborah influences Linda, Brian, and Fred. Maybe Deborah's the mom, I don't know. What about Yvonne and Brian? They influence each other. Computer sciencey one, a module dependency graph. Your main module, which in the tree would flow down to display a parser and whatever protocol means to interface with other networks and so forth. Very often you find this when your software grows, that you're looking for some sort of dependency graph here. And I imagine many of you have dealt with things like NPM. Does that ring a bell for some people? Where you go online, you get libraries and you find that they're dependent on other libraries.
Yep.
That's what we're talking about here. Also, this type of graph is special. It's a tree. We're going to define what a tree is as a special case of graphs. Graphs are larger than that. A tree would be some kind of subset. Trees have certain features that we want to define. Well, this one, a niche overlap graph in ecology, where you talk about competition between species, and each species is represented by a vertex in the graph, an undirected edge. So these edges here don't have an arrow connected to them. Connects two vertices if the two species represented by these vertices compete. So the opossum apparently is competing with the woodpecker for food, and the woodpecker with the shrew, but not with the mouse, etc. Okay. All of these graphs have commonalities to them. They have basic features that are mathematical, and we want to start getting used to those and learning the basic vocabulary. And tonight, I just want to introduce you to that. So I'm in section, bad pen. Sooner or later, I'm going to have to leave the house just to get a new pen, more ink, or I'll have to stop and say, that's it, no more ink.
The privilege.
Okay. 10.1, Introduction to Graph Theory. I know some of you are thinking, ink, who uses that? That is so 20th century. All right. Intro to Graph Theory. Basic definition. That any graph in general, G, is formed by two sets. Number one, set V, and we indicate it this way, V of G, which is a set of vertices. And number two, the edge set, E, and this is just the notation here, it doesn't actually mean like a function, but EG set of edges. Visually, your vertices would be the points that you saw on those examples, and the edges would be the arcs that connect the points. There's more. Each edge element has one or two, we'll call these quote unquote endpoints. That are elements of your vertex set. But that makes sense because what's an edge? As you saw my pictures, it was some sort of arc or a line that we'll say connected 2 points. So we want to say that each edge is going to have two of these endpoints, or maybe just one if the edge circles back and forms a loop and comes back to the same point. Now, the way that these edges and vertices are related to each other is given by one other feature of your graph, that edges and vertices correspond by this thing, by an edge endpoint function. There's an actual function for which the domain is the set of edges, and we're talking about f of e of I. The codomain would be a set of endpoints, either 1 or 2. Okay. Now you have to see this in action. It's one thing to see the visualization of the graph and see the vertex points and the edge lines or arcs or whatever. It's another thing to define it mathematically so that you can process it, you can create theorems about graphs, or define it mathematically so you can program it, so you can code this thing. And that's why you need these things. You need 2 sets for your edges and vertices, and then you need some kind of function that relates the 2. And you'll see that in my next example here. So here's number 1. Graph H. There's a vertex set, V of H, which will equal 5 vertices, which we will just label V1, V2, V3, V4, and V5. Then there's an edge set. And we'll have 4 edges for our graph. E1, E2, E3, and E4. If you want to visualize this, you can imagine the 5 vertices as 5 points, and then you have 4 edges that are connecting, relating those points together somehow. But you can imagine there's lots of ways that we could relate the edges. If there's 4 options here, there's all kinds of ways this could happen. That's why you must have this edge endpoint function to do that for you, to put the 2 together. So here's our edge endpoint function. Which I'm going to define by a table. E1, remember the edge endpoint function associates each element of your edge set with a set of vertices. E1 is associated with V1. E2 with V2 and V3. Edge 3, V2 and V3. Notice they're the same. And then edge 4 with V1 and V5. And that's it. That is your graph H. It's all you need to work with it, to do whatever you want to do with it. Code it. Most likely, though, for what we're going to do, to visualize it. We want to have a look at it. We understand this graph because there's lots of things that are happening in here, but without a visualization, it's pretty hard for us as humans to get a sense of what's going on. So I want to visualize it now. How many vertices? 5 of them. I'm just going to arrange them. And when you do this kind of work, your vertices are arranged typically in a circular pattern, or if there's, say, 4 of them, you'll make a square. Sometimes you'll put them in a line because it fits the problem better. It just depends on what you're doing. And for what we're going to do, we're going to have very small vertex sets in the real world of graph theory, these are monster things. They can be the network of millions of vertices and so forth. But for our understanding of graphs, we're going to keep things very simple and small. Okay, so I'm going to have V1, V2, V3, V4, and then V5. And now I have to visualize the edges. So I go to my edge endpoint function and say, what about E1? What's going on there? E1 is associated only with vertex 1. That tells me that vertex 1 has an edge that forms a loop like that. That's E1. I don't put an arrow in here because it's not what we call a directed graph. Oh, by the way, we're going to get to that, probably not tonight, so I'll mention it. What if I did want some kind of arrow with my edges? Well, look at E2 here. Now, what is this saying? I got to set V2 and then V3. So edge 2 is relating V2 to V3. Those are the two endpoints for edge 2. But what if I wanted to send it from V2 to V3 with an arrow? Then what I would include in here would be an ordered pair. I would say first V2, then V3. And if I wanted to have it go the other direction, it would be first V3, then V2. So we can handle the directed graph issue by adding ordered pairs into our edge endpoint function. Anyway, what's E3 here? It's V2 and V3. And then E4 is V1 and V5. Okay. And that's it. What about V4? It's an orphan, just hanging out there. There's no edge that's related to that one. Okay. There's your first taste. Can you see that pretty clearly? You could take the graphical visualization here and work backwards to get this. If you needed to, you'd start here and create this. We are very rarely going to do this. This is just to give you the idea that underneath any visualization, there is the technical definition. There's a set of vertices, there's a set of edges, and there's going to be an edge endpoint function. But it's too clunky to work with that. It's much nicer just to have your diagram and roll with that. Let me give you a little more thought to the diagram business here. Number 2. And this is actually from one of your book exercises, but I don't see it where it is. Anyway, here we go. Let's have a given graph here. Graph G, but they'll usually be presented in the diagram form. And this was V1, V2, V3, V4. This is E1, E2, E3, and E4. Okay. Hey. You guys all see what I got there? What is f of E1 equal to?
V1 to V3.
Yeah, the set.
Set, yeah.
V1 and V3. B. Redraw without intersection. So, is it possible to put this together without having these two edges appear to intersect?
Just flip like V2 and V3.
Yeah, can you imagine that you pick it up and then the V2 and V3 you just reverse, you like untangle it, if you will. You guys see that? So you could do it like this. You could say, here's V1, and then over here now will be V3, and then V2, and here's V4. And let's see, V1 goes to V3 by edge 1. And then V2 and V3 are connected with an edge 3. I missed E2. E2 is V2 and V4. And then this one here from V1, that's E4. You see? My point here is there's different ways to visualize the same graph, and some ways are much more informative than others and easier to follow. You're not necessarily going to get this intersection here. Now, there's a certain kind of graph that you can't do this to. You can look at it and say there's no way to undo it. We're not going to go there. I'm just saying that that's one of the interesting problems that occur in graph theory is like, well, what kind do that, some, what don't? You can get weird about this too if you wanted to. You could stretch these all over the place and have some very odd looking diagrams. You typically want the nicest one you could get though. Oh my goodness. I'm running out of time. I thought I'd get to this one. Okay, you know what I'm going to do is I'm going to just come back to, next time I'm going to present kind of quickly an overview of the vocabulary here. And so I'm going to give you guys a little bit of assignment here between now and Tuesday. Please read over, just skim over the 10.1 material just to get a bit of the vocabulary involved in these graphs. Let me put on the screen here what I was going to develop with you, and I think it just saves some time to show what I'm talking about. That I was going to develop a graph like this and talk about some of the terms we use. See, for example, right here, well, this is an obvious one. This is a loop, this edge. But when we look at V2 and V5, what do you see here? There are two edges that connect both V2 and V5. Then we would call these edges parallel. V2 and V3, here we go, they're adjacent because there's an edge that essentially connects them, that there's an E6 that relates V2 to V3. So we say V2 and V3 are adjacent. V1 is adjacent to V3 via edge 7. This vertex right down here is what's known as an isolated vertex, etc. Lastly, there's the degree of a vertex. The number of edges incident on the vertex. So that's an easy thing to see instead of using the language. Look right here at V2. What's the degree of V2? 1, 2, 3, 4. What's the degree of V3? 1, 2. What's the degree of V1? 1, 2, 3, and actually 4. Loops will count as degree 2. Then you can talk about what's the total degree of your graph. What's the degree of V4? 0, etc. And we'll develop some theorems about degrees and all of that. I'm looking at the clock saying we're in pretty good place here. Again, you should look over 10.1 just to get comfortable with the vocabulary. It's pretty easy to follow along, and I'm going to say that's enough for tonight. Don't forget your homework due Monday night, not Tuesday. I want it done before we come to class. Jeremy's already clapping his hands. He's ready to go. All right. I'm going to do this. I'll say goodbye to everybody, and I'll be hanging out. If you want to have a chat afterwards, I'll stop the recording. But bye-bye.
That's good. Thank you so much.
All right. Thank you so much.
Okay. I'll be hanging out here. Let me turn the screen share off and stop the recording. Let's see.